Hello everyone, we are here with Physics 2211 Lab 5, Achieving the Free Falling Record. We will examine a jump by Felix Baumgartner, which was a drop from over 120,000 feet. Now, we're going to have a couple goals for this lab. Our first is to analyze the motion and understand how he achieved a drop from so high up. We're going to understand how the velocity changes and the time of the drop, and additionally, if he breaks the sound barrier and if he reaches terminal velocity. And then we want to determine if the computational model is accurate. And a quick look at our results, we do determine that he does reach terminal velocity, that in the model it says that he experiences terminal velocity and he breaks the sound barrier. Additionally, we can then see that there is some reflection between the computational model and the actual jump. To begin with, we have some important concepts, which is first we have to model the forces that are on him. First, we see that there's gravity due to the Earth, and then also drag force, which will be very helpful to determine how he increases his speed and then also how his speed decreases after a certain point. Then we will use the momentum principle to update the position and velocity by taking the F net and determine what the F net is each interval and then updating it. So to begin with, we had our predicted model, which some initial conditions. Our first is the system, which is the human, and then we have the surroundings, which is earth and the air, which helps us determine the coefficient of a drag. And there's going to be two in this case because we have one where he has a low coefficient due to drag because there's little to no air pressure. And then we have one where there is a coefficient of drag when he reaches the Armstrong's line or Armstrong's limit. And then we have our initial conditions, which is 39,000 meters high he started with, the start time, and then change of proportionality constant, which is the Armstrong's limit, and then the final update occurs at 269 seconds. So pretty much we have to use the position velocity update, which we've used in a lab before, but we now have to model it in two different cases. And that means that the D changes in the first case is different from the D in the second case when he passes the Armstrong's limit. And pretty much we just find the F net on the object, calculate the object's velocity, and then update the new position as he falls through the air. So these are pretty much our results from the model. We can see that he does experience a very high velocity to begin with, and he kind of increases up until that point, but as soon as he reaches 80 seconds, it pretty much changes drastically downwards because now there is a strong air pressure and he no longer has just a low coefficient of drag. So pretty much what we can predict is that Baumgartner does break the sound barrier. He reaches it around like 18,000 meters high in the air. And then we do see after that, he reaches terminal velocity in the model, which is anywhere above 17,000 meters until when he pulls his parachute at around 5,500 at 260 seconds. Now, there are some sources of error because we do know that we can't calculate the exact drag coefficient at every interval because we would need to update the density at every point. And then we also know that he could be falling faster or slower based on his surface area, and we didn't really know how to change the Armstrong line over a longer period of time, so it was very instantaneous, which is not supposed to be how it is. Now, the actual data is here, and for the most part, it was the same, besides that his terminal velocity should not have been reached, and that's just due to us not being able to change the air density constantly. Finally, we have our what if and what does it mean questions. So, what happened if he jumped head first? Well, if he jumped head first, the velocity would be a lot greater, and that means when he reaches the Armstrong limit, his change in velocity would be very high, meaning that he could experience a very high impulse, and that could have a lot of implications on his suit and body. And then also, why did he never reach the terminal velocity? Well, as we can see, as he falls down, the pressure increases, and because it's never constant, it's always increasing. He constantly achieves a different velocity, and he never reaches terminal velocity as drag is increasing. Thank you.